Hi folks, welcome back to Physics with Captain Rod. The purpose of this video here is to again demonstrate how to use method of components to add vectors. So what we're looking at is we've got a pair of vectors here. I've got vector A, which makes a 35-degree angle with a positive x-axis, and it's 10 units long. Here's a second vector, vector B, 14 units long at an angle of 60 degrees clockwise from the negative or from the positive x-axis. And what we're going to do is find the resultant vector, which is the vector sum of the two. Now, it does not matter for this example what type of vectors these are. They could be position vectors, force vectors, electric field vectors, magnetic moment vectors. There's lots and lots of examples. All vectors are handled the same way regardless of what type they are. Now, first of all, I'd like to talk a little bit about the picture. Right now, these vectors are tail to tail. Graphically, when vectors are added, they need to be tip to tail. You don't always have to redraw your picture, but I'm going to go ahead and demonstrate what would that look like in this example. So what I'm going to do here is I'm going to draw another picture. I'm going to take this vector, vector A, and I'm just going to basically copy it. And put this over to the right here. Then I'm going to do the same thing for B. There's vector B. Actually, I'll go back and include the label there. And what I'm going to do is I'm going to take B and I'm going to place it so that the tip of vector A is touching the tail of vector B in my new picture. Get this label moved here. We don't need that right there. There, that's good enough. All right. So now I've just rearranged these so that the tip of A is touching the tail of B. Now I also could have drawn B first, and this would be going down and to the right, and then put A on the end of it, which would put that right here. It doesn't really matter which one we draw. This method is called the parallelogram method because if I drew both of them, I put vector B in here and vector A, this geometry that you would see would be a parallelogram. I find that there's no reason to go through and do both of them. Now I'm going to draw the resultant vector. The resultant vector starts at your starting point and ends at the tip of your last vector. Now I say last, here there's two vectors, A and B. If there were a third one or a fourth one, you put it at the end of the very last vector. I'm going to go ahead and draw in my resultant vector. And I usually label it R for resultant. So here's vector A, here's vector B, here's the resultant vector. Now, what we could do is we could use like law of sines and cosines on this triangle, but we're not going to. We're going to use method of components because law of sines and law of cosines work pretty well when you're dealing with two vectors and a resultant, but it gets difficult in a hurry when you talk about three vectors and a resultant or four vectors and a resultant. Method of components works very, very nicely no matter how many vectors there are. Now, here's vector A. And vector A can be drawn in component form. And I think what I'll do is draw those in the original picture. And I'm going to draw these in red. The x component of vector A looks like this. And if I were doing this, I would call that AX. X component of vector A. The y component of vector A looks like this. So there's AY. You can draw them in this picture as well. The reason I chose not to is this picture was going to get muddled up pretty fast, so I just went ahead and drew those components in my original picture. We can find these components because this is a right triangle. Now, this is very important to realize. You have to tunnel vision on everything except this triangle right there that I just outlined in green. AX, that's this guy, is adjacent to the 35 degrees. So I can come down here and calculate that easy enough. Cosine 35 degrees is equal to AX over the hypotenuse. I'm just going to go ahead and put 10. So AX is equal to 10 times the cosine of 35 degrees. And I'm going to take a moment here and ask one of my helpers to give me a numerical value for that. What's it come to? Thank you. So this is approximately 8.19. All right, we can find AY by using the sine function. The sine of 35 degrees is equal to AY over 10, because sine is opposite over hypotenuse, and that side is opposite the 35. So AY is equal to 10 times the sine of 35 degrees. Would somebody please give me a value? 5.76. 5.76. Okay, so I'm going to go ahead and write these numerical values down here. We know that this guy right here is, whoops, 5.76. AX we found to be 8.19. Right. Next, let's see, I'm going to get rid of this now. Whoops. Before I do, I'm going to save this. Now, we don't need this anymore. All right, now we're going to start working on vector B. And I think what I'll do to differentiate them is I will draw vector B's components in blue. So vector B, if I draw its x component, I'll draw this down here just a little lower. The x component looks like maybe about that. Then the y component, looks like I drew that x component a little long there. Y component maybe something like this. Now components themselves are vectors, so they get arrows. Drew that just a little long. All right, so here's vector B now, 14 units long. This blue component is opposite, or I'm sorry, is in the y direction, so I'm going to go ahead and call that BY. This component is in the x direction, so I'm going to go ahead and call that BX. And now I'm going to go ahead and start working on finding those. And again, the key to these problems is tunnel visioning on what we're working with. So right now the important triangle is this one in green. So you need to be able to just get everything else out of your mind except for that triangle in green. The cosine of 60 degrees is equal to the side adjacent, that's BX, divided by the hypotenuse, which is 14. Somebody please take cosine 60 times 14. 7, okay. I'm going to go ahead and just store that over here. This guy is equal to 7. Remember that was BX. Boy, that's hard to read. BX 7. We can find BY by the sine function. Sine of 60 degrees is equal to the side opposite the 60. That's this, BY, over the hypotenuse, which is 14. Would somebody give me 14 times the sine of 60 degrees? Just give me 14 sine 60. 12.1, thank you. Go ahead and store that, 12.1. All right, we don't need this anymore. Let me save that. All right, we don't need this work anymore. All right, we have everything we need now to come back here and focus on this picture. Here's our resultant. The resultant itself has an x component and a y component. I'm going to go ahead and draw these in the picture here in green. Now whether I go over and down or down and over doesn't really matter. To keep the picture clean, I'm going to go ahead and draw this down and over. Except I'm going to go back and use my straight edge ruler because it gives me these nice vectors that are a little easier to on the eye. All right, maybe something like this. we go. All right, so this one right here is the one I'm calling Rx, the X component of the resultant. This one is the one I'm calling Ry. That's the Y component of the resultant. You don't necessarily have to draw these in every single problem. I'm just showing them in this picture. Could have also went over and down. Could have also just cloned this resultant vector maybe down here and drew it with its components all by itself. But all right, the important thing now is how to find those vector components, these things. All right, I'm going to start with Rx. You get the X component of the resultant by adding the X component of all the vectors you're dealing with. So I'm going to look back to vector A. The X component of vector A is here, and we found that to be 8.19. And then here's vector B. Here's the X component of vector B, which we found to be 7. Now, you'll notice that both of these components, the red one and the blue one, they point to the right, and I've got the positive X direction pointing to the right. That's why it's plus and plus, and these add to 15.19. Okay. The Y component of the resultant, right, that's this one, we get by adding the Y components of all vectors involved. So I looked at the two vectors involved, this picture on the left. Here's vector A. Here's its Y component, 5.76 in the positive Y direction. So this is going to be plus 5.76. Now we take a look at vector B. Here's vector B. Its Y component is this one. And it's 12.1 units long, and it's down. The direction needs to be taken into account, and we do that with a minus sign. Because this points in the minus Y direction, this is going to be minus 12.1. Would somebody give me 5.76 minus 12.1? Minus 6.36. So I'm going to take a moment here, stop, and just kind of overview the really important parts here. The original first two vectors, A and B. Graphically, when you add them, they need to be tip to tail. You don't always have to redraw it every single problem, but I do for some of them. So what you would do is you pick up vector B, put it at the end of vector A, like I did in this picture. Could have also picked up vector A and dropped it on the edge of vector B, so that the tip of one vector is touching the tail of the other. Then you can draw your resultant, which goes from your starting point to your end point. Next, you take all of the vectors you're dealing with and you break them into X and Y components, or maybe some other component directions depending on the problem. But now you can do this in the original picture. Well, I'm sorry, you can do this in your new picture or the original picture. Or you can draw these separately off to the side and do them. Doesn't really matter. But what you do have to do is you have to figure out the X component and Y component of the first vector, X component, Y component of the second vector. And then if there's a third vector, you would find the X and Y components of the third vector. Next, the resultant itself, regardless of what direction it points, it will have X and Y components, and conceivably a Z component if it's a three-dimensional problem. You find the X component of the resultant by adding the X components of all vectors involved. You find the Y component of the resultant by adding the Y components of all vectors involved. You take plus and minus signs into account with your coordinate system. I've got right positive, up positive, and that's why these are plus and plus. Vertically, we have up positive. That's why this one is plus, but this guy is pointing in the minus Y direction, and hence the minus sign. Okay. All right, so now we have Rx, Ry. I'm going to go ahead and write these over here. So Rx is 15.19, Ry minus 6.36. Now this minus sign right here, in my view, that sign is optional. Vectors have a magnitude and a direction. We know the magnitude is 6.36. We know that the direction is down. Because I have that arrow pointing down, I don't really need this minus sign. The direction is stored in that arrow. If I were grading somebody's paper and somebody had 6.36, as long as they have that arrow, I don't take off any points. Somebody else, or I'm sorry, if they had positive 6.36, as long as they have that arrow, I don't take off any points. Somebody else may just leave off the minus sign. Again, as long as they have the arrow, I don't take off any points. Now, as far as how do we add these? Well, these are added by Pythagorean theorem. I need to get rid of this. And the key is recognizing the triangle we're working with, right, is this triangle now, right there. And again, it's a right triangle. So the magnitude of the resultant squared is going to equal 6.36 squared plus 15.19 squared. The minus sign here is optional because by the time you square it, it's positive anyway. If you do put the minus in, make sure you have parentheses and it's inside those parentheses, otherwise it's wrong, not written correctly. Would somebody please find the magnitude of that resultant for me? What's it come to? Thank you. Okay. 16.47. Let's go ahead and get an angle. Now, I'm going to go ahead and find this angle, theta. The tangent of the angle theta is equal to opposite, 6.36, over adjacent, 15.19. Do not include a minus sign with the 6.36. I'll talk about here why not in a minute. Would somebody please give me the inverse tangent of that ratio? Inverse tangent of 6.36 over 15.19, please. 22.7. 22.7 degrees. Now, you'll notice this angle is 22.7. That makes this angle also 22.7 because these lines are parallel. So what I'm going to do here, I'm going to write out my answer. The magnitude of the resultant is 16.47. And then I'm just going to draw a picture. The resultant is 22.7 degrees down from the positive x-axis, or clockwise from the positive x-axis. I'm just drawing a picture here to make it absolutely clear what angle that I'm giving for my direction. So the purpose of this video was to demonstrate how to add vectors in 2 dimensions by method of components. I hope that it helped do that. Have a great day.